Hello and welcome back to College Algebra, MAT 150. In this lecture we will be discussing the fundamental theorem of algebra and conjugate solutions. So the fundamental theorem of algebra states that every polynomial of degree n, so sometimes we may call it like p sub n of x, n is a integer and is greater than or equal to 1, has at least one zero in the set of complex number. And we can say this one of two ways. We can say that either it can be written as n, so there's an n number of these factors that are linear and have solutions in these c values are in the complex numbers. So remember, a complex number is of the form a plus bi, where a and b are real numbers, so 2 plus 3i, something like that, and I is the imaginary number I equal to the root of negative 1. So you can write all these where the c's can actually be expanded to be that if we want. Or we can say that it is a product of linear factors and irreducible factors, with those coefficients being in the real numbers. So it may not necessarily be written as all linear factors if we don't want to have these imaginary solutions. So as it turns out, if you have solutions that are complex or irrational for zeros, so if you have complex or irrational zeros, you will always have an accompanying conjugate solution. So what do I mean? So if we have the 3 plus 2i, then a conjugate solution might be 3 minus 2i. So again, this is a complex number. We have a conjugate. Basically, the conjugate part just means that you have a minus in between. Or if you have a rational number, or irrational number rather, so if you have the root of 3, your conjugate may be negative the root of 3. So if it's in front of the I or if it's in front of the root, that's what changes when you go from the first one to the conjugate. Okay? So with that being said, let's try to construct a degree 3 polynomial with zeros of 1 and 3i. So what do we mean by a zero? Remember that means that we have solutions for the when the whole polynomial equals 0 of x equals 1 and x equals 3i. Now remember that if we have complex, so x equals 3i is a complex number, we always have a conjugate solution. So x also equals negative 3i. So this is a conjugate of the previous one. And what we want to do, if we want to construct a polynomial of degree 3, that means that we have to look at the factors. And we have to have at least these three factors to make this work. So what can we do? Well, we can work backwards. We try to get one side equal to 0. So we're going to subtract 1 here. So x minus 1 equals 0. Subtract 3i here from both sides. X minus 3i equals 0. And then add 3i in this case to both sides. So we get x plus 3i equals 0. And these are the factors. So polynomial of degree 3, well, if we just take x minus 1, x minus 3i, and x plus 3i, that would multiply to be a degree 3 with a leading term, as a leading term. And each one of these would be factors. Now, usually we want to write these without irrationals. We want to have them all have rational coefficients. So what we're going to do is, at the very least, we want to make sure these get multiplied. Now this, we have x minus 3i times x plus I, is an example of an already factored difference of squares. So remember, a plus b times a minus b is the same as a squared minus b squared. So what does x minus 3 times x plus 3 actually multiply to be? Well, it multiplies to be x squared minus 3i squared. So we're just multiplying these two right here. And if we start to simplify, x squared. If we square 3, so minus 3 squared is 9. I squared. But remember, I squared was the root of negative 1. So I squared then is negative 1. So if we square the square root, that goes away. And what we actually have is this I gets replaced, I squared gets replaced with negative 1. So we have x minus 1 times x squared. Negative 9 times negative 1 is just positive 9. So that's what this actually multiplies to be. Okay, we have polynomials. We have a linear factor, and this is what I mean by an irreducible quadratic. So you can actually factor it with, if you really want to, but with real numbers it's unfactorable. All right, so that's one polynomial we've constructed. We can also construct a polynomial of degree 5, like in this next example, that has zeros of x minus x equals negative 1. We also have a 0 of x equals 4, and we have a 0 with x equals 0. So remember, we're trying to get one side equal to 0. This x equals 0 already has one side equal to 0, and we know that it has to have a multiplicity of 1. Okay, so we're done with that. One side isn't 0 here, so we have to subtract 4. So x minus 4 equals 0. And this, in this particular case, it has a multiplicity of 1. So 4 has a multiplicity of 1. Again, that refers to the power, so I'm just going to write it multi 1. And this x minus 1, we need to add 1 to both sides. So we get x plus 1 equals 0. This has a multiplicity of 3. So what is our polynomial of degree 5? Well, does 3 plus 1 plus 1 equal 5? It does. So we have x plus 1 to degree 3, x minus 4, and then we also have just x. So since x equals 0, and traditionally we put x out in front. So x times x plus 1 to the third times x minus 4 is a basic polynomial that has all of these. It's degree 5, and it has those zeros with those multiplicity. All right. One more example we could take a look at. So now in this instance, we want to find a polynomial of lowest degree with rational coefficients that has the zeros negative root of 3 and 1 plus I as two of its zeros. So we know we want to write this without any rational or complex numbers. So again, just like what we've been doing, fx equals negative the root of 3 and x equals 1 plus I. So those are zeros. But remember, for each of these, they have to have a conjugate. So x equals, so if this is negative the root of 3, the conjugate is positive the root of 3. If this is x equals 1 plus I, the conjugate is x equals 1 minus I. So we'll highlight what which ones are the conjugates. All right, and then we try to get these as factors. So x minus the root of 3, x plus the root of 3 equals 0. X minus 1 minus I equals 0. X minus 1 plus I equals 0. And now we have these four factors. So these must be our degree. So we're going to actually have a polynomial of degree 4. But it's x minus the root of 3 times x plus the root of 3 times x minus 1 minus I times x minus 1 plus I. All right. So how do we handle this? Well, we're going to multiply this together and this together. This is very clearly a difference of squares. So we can just write that x squared minus the root of 3 squared. But this is a little bit different. What we're going to do is we're going to treat this as one number, and this is another. So it's like we're multiplying two binomials. So x squared, x times x, and then x times all this, so plus negative 1 plus I x, and then plus x times negative 1 minus I x, and then lastly plus negative 1 minus I times negative 1 plus I. So we have 1, 2, 3, 4 terms here. So let's continue simplifying. Here we get x squared. The square of a square root is just itself, the number on the inside. That one's the nice and easy simplification. Not much simplification to do here, but here we have negative 1 plus ix, and then negative 1 minus ix. So we're adding the ix part, and we're subtracting it out. So we're left with minus an x and minus an x, so this becomes negative 2x. And here we're just going to multiply this out to be able to see it. And this is a difference of squares. So negative 1 minus I times negative 1 plus I. So we get negative 1 quantity squared minus I quantity squared. We will indicate the stop of the whole thing there. So we have x squared minus 3, x squared minus 2x, plus negative 1 squared is 1, minus I squared is negative 1, so plus 1. So this actually becomes something that's much more manageable, x squared minus 2x plus 2. And this is a polynomial. It's of degree x squared and x squared of degree 4. And so that's the lowest degree that we could possibly have, because we're required to have the conjugates as solutions as well as what we were given as zeros. So this concludes this lecture.